When we're describing data, it's really important that we talk about the spread of the data, how far away from the center the data points are, and if they're all on the top end or are they all on the small end. So we have some ways of measuring that, measuring the spread of the data. And the first one we're going to talk about is standard deviation. This is used in every field, it seems, and standard deviation just gives us a numerical measure of the variation in the data. By variation in the data, we mean that we're going to compare the data pieces to the mean and see how far they vary from that mean. Then we're going to calculate this number called standard deviation. You may have heard it used before. People, when talking about numbers of data, talk about plus or minus 1 standard deviation. That is a figure that will make more sense to you, hopefully, after this course. A couple of things to remember about standard deviation. It's always going to be a positive number because it measures the distance of a data point from the mean to where that data point is. So distance is always a positive number. So our standard deviation will always be a positive number. And if it's very small, then it's very close to our mean. If it is a little bit larger, then it is further away. So that much we can just kind of know intuitively. It can also be used to determine whether, and I already said that, whether it is close or far away from the mean. So we're talking about spread and measuring the spread of the data. So calculating it, the formula looks rather scary. So I'm hopefully walking through it and then maybe showing an example of how to do it manually. Also, calculators and computers now just do it beautifully. But we're going to call each of our data points X. So I'm going to just underline that for a minute, X. And so we're going to take each of those data points and we're going to compare them to the mean. So in both of these formulas, this one's for the sample and this one's for the population, and they are really identical. We just use different letters to represent these numbers in populations and samples. So we're going to be adding up. Right here we have our adding up mark. But what are we adding up? We're adding up each data point subtracted or subtracting the mean. This mean right here with our little hat on it, and that hat's way up in the air, it should be down closer to the X, is called X bar. And that is the mean of a sample. Down here we have X, and we're subtracting mu from it. Mu means the mean for a population. So these two are very, very similar. They're the exact same things, except one is for a sample and one is not. So we're going to take, back up to this area, we're going to take each data piece and subtract the mean from it. This will give us the distance, right? How far away from the mean each piece of data is. That's called our deviation. And in a data set, there are just as many deviations as there are items in the data set, because we're going to do this for each piece of data. The next portion of calculating the standard deviation, once we do that, is to square. Notice on the outside of both of these I have squaring that. So after I have all of the pieces of data, subtract the mean from them, then I'm going to square that resulting number. I think on the next, if you kind of remember this or write it down or have your book handy and look at the next screen, this is how, if I do it by hand, I'm off the screen, sorry. I'm going to move myself a little bit further off. Here's my data points. Give me a pen here. My data points, each piece of data, and again, we call those X. Frequency enters in if I have a frequency going on with it, so we'll have to have frequency sometimes. But I'm going to take my deviation, X minus X bar. Whatever it is, I already figured out from my data points is my mean. Then I will be taking 9 and subtracting the mean from it. In this case, my mean ended up being right there, a minus 1.525 with this particular data set. So I am going to be subtracting that mean from all of my data points. We're going to kind of ignore the frequency right now, but I just wanted you to see that part of the formula. My x's, and then I subtract my means. and then I'm going to square that number, and I get a whole list of them. Then I take that number, and if I am talking about something that happens more frequently, I will add in the F. In the formula, that is not there for right now, but that is what I add up. Remember, I'm going to go back to that slide. Remember that summation notation that was there? That is what I add up after I take each data piece and subtract it, and then square each one. I'm going to get a list. That is what I add up. So going down now, moving my face a little bit to this blank spot maybe, and sliding my stool over a little bit. There we go. So that sum that I finally add up in that final column is going to be the top part of that standard deviation formula. That is going to be divided by n or n minus 1, depending on if it is a sample or a population. So let me just go in here, divide it by the number of data points. If it is a population, let me add a, that makes more sense. Or if it's a sample, we're going to do n minus 1. So in this case that it's showing us here, we get that number, and we're going to divide by n minus 1 because it was a sample. And we get this new number here. This is not quite yet our standard deviation. This is called our variance. It is the standard deviation squared. All we need to do with that number is to take the square root of it to get our standard deviation. In this case, it is a small s because it is a sample standard deviation. We could have, I'm going to go back to the formula here just to show you the notation. We could have it be theta, which theta is going to be standard deviation for a population. So that's just a difference in marking. If we do it on the calculator, which you probably will want to do, we are going to, on the graphing calculator, something like the TI-84. There are a lot of graphing calculators, but the TI-84 does have a simulator that you can put on your cell phone. I think on the iPhone, the simulator costs maybe $4 or $5, but on the Android, it is a free download app. And just look for an emulator for the TI-84. I would search that. So you go to the stats menu, which on most calculators that are set up like the TI-84, it's going to be on that second row of buttons, the row that starts with the alpha key. Third button in says STAT. Push that, and this is the menu you'll see. When we want to enter into some data, we will want to go ahead and click the edit button there. That will help us to enter our data. And if we wanted to sort it for finding mean and mode, we would sort it ascending, that's what the A means, from smallest to largest, or we could do largest to smallest. We can also clear the list if we want to start with a new data, but that is what is involved in that edit menu, and that's where we want to go to enter our data. The next slide will look something like this. In this case, they already have entered data for two different lists. List 1 is here, and list 2 is here. Notice that they look like they're actually still adding on to list 2. I would try to keep it clean. If you don't need two lists, sometimes you need to have two different lists. I would just keep everything in list 1 and clear off the other lists, but input your data there. After your data is input, you're going to go back to that stats menu. And this time under stats menu, you're going to go over, instead of edit, you're going to go to the calculate. Calculate and make sure one variable statistics is highlighted, and you push enter there, and then you get a screen that shows you a bunch of different things. X bar is going to be my mean. Okay, X bar is my mean. The sum of all the x's is simply the sum of all my data points. The sum of all the x's squared is simply the sum of all the x's squared, which is needed in some calculations. Here we have the standard deviation of a sample. That's why it has the S. And here's the standard deviation for a population. It has our theta. So notice they're a little different, but not a lot different. And this N means that there were 26 data points that you entered into that list. This arrow means that you can scroll down and you can get some other information. I believe the range is there, or the minimum and maximum, some other things that you might be interested in. But this is the standard deviation of the population if it was a population, and this is a standard deviation if it was a sample. So you can easily find it on your calculator. Again, some practice helps. There are lots of YouTube videos that tell you how to find it on a graphing calculator. And I imagine if you use some software on the computer, it will walk you through the steps as well. As long as you have your list of data, you can get your standard deviation. So what do we do with that, right? Once we have our standard deviation, if we're going to be comparing, we're going to talk about one more formula and number here. If we're going to be comparing different data sets, it's a little bit harder to compare if they're completely different. So standard deviation is useful when comparing the values because we could say it's 1 or 2 standard deviations away. But to make this all normal, we come up with something called the z-score. And the z-score is fairly easy to find. It is simply, here's a little bit of it right here, the number of standard deviations. We're going to take our value, those are our data points, subtract our mean, and divide by our standard deviation. So I think that I have formulas on the next slide to look at a little bit. Yes. So for the number of standard deviations, this is often called the z-score, and we're going to use the symbol z. In the symbols, the formula becomes, these two things are the same formula, they're just in different forms. If you remember from algebra, we can always change forms of a line. This one is solved, the first one is solved for x, the second one is solved for z. But we will use both forms eventually. But the z-score equals each data point minus the mean divided by your standard deviation. The top one is for sample, the bottom one is for a population. So that gives us a z-score that then we really can compare. We've normed it, right? We are talking about the same thing then with these z-scores. So it doesn't matter what the data points look like, we can have this central talking point, which is why we do find the z-scores. So we'll be using those later on, but that is the math part of it. There are a couple of rules that are handy. Chevsky's rule for any data set, no matter what the distribution of the data, at least 75% of the data is within 2 standard deviations of the mean. At least 89% of the data is within 3 standard deviations of the mean. And at least 95% of the data is within 4.5 standard deviations of the mean. This is Chevsky's rule. There is also another rule that we use. This is good for just quick calculations. So the other rule is the empirical rule, and it states, I'm going to stick my head way off the side here, that approximately 68% of the data is within 1 standard deviation of the mean. Now when I say that, think of the mean in the middle here, and on either side I have 1 standard deviation. So I go over here to the mean and then over here to the mean. So I'm talking about 2 areas, one on either side of the mean, each a standard deviation wide, whatever that standard deviation is. Maybe the standard deviation comes out to be 4. Then I'm talking about from the mean to one side 4 and to the other side 4. So that whole spread is going to be 8. So within that spread, the empirical rule tells us that 68% of my data is in there. That's kind of important. That means most of my data, right, is in between that 1 standard deviation on either side of the mean. And then we go out 1 more on either side. So now here we actually have 2 over here and 2 over here. So we have 4, the width of 4 standard deviations, and that's 95% of the data. Go out 1 more, and it is about all the data. There might be some outliers. So empirical rule is a little easier to remember than Chevsky's. I'm going to flip back up to Chevsky's. Here we have, it says that 75% of the data is within 2 standard deviations, 89 is within 3, and 95 is within 4.5. So it's a little bit different, Chevsky's and the empirical rule. Usually we use the empirical rule as we are doing calculations. It is easier and more straightforward, we think. This is for bell-shaped data and symmetric data. On Chevsky's, it is for any data set. Mostly what we'll be working with, because this is Stats 1, will be our bell-shaped data and our normal data. So we can use the empirical rule for almost everything that we do. That was a lot of information. Good luck working through the problems and taking the quiz this week, and let me know if you need me.